Hey, many years ago I found this trailer by accident. And when I say by accident, at the time I played a little bit of Rainbow Six Siege, so YouTube thought that I wanna watch more Tom Clancy content. It was the Tom Clancy Ghost Recon Wildlands reveal trailer 2015 Europe E3. I guess the order is wrong. I have a bad habit of reading comments, so I do this here as well, where a bunch of people timestamped out a specific section. Is still the greatest transition I have ever seen. Decent transition, good transition, mega transition. That transition though, the greatest transition I have ever seen. This makes me curious what makes this transition so good, so I jumped to this specific section and I saw it. It was beautiful. Oh, hey, just a minute, okay? We will continue, just a minute, okay? Thanks. If you wanna watch the original trailer, you can find the link at the description down below. And if you are already there, no pressure, there's a bunch of other cool buttons as well. For example, this subscription button. Look, super cool. Or if you wanna skip my yapping session for the next god know how long, there's also a Medium article just for you. Describes how I made this effect in a written form instead. Beautiful. I mean, yeah, sure, the transition is really good, but you might already know where this is going to end up. I really liked how the no, there's no way. What else? Oh, flour, soak up the water. I immediately tried to recreate this effect, but my smooth brain just can't handle it, so I put this one with many of my other ideas into a drawer and move on with my life. Until today, because today I'm going to recreate this effect. But before we jump into that, let's break down what we can see and try to understand it. What is going on is once the fluid contacts the substance around the contact area, it starts to soak up the fluid. I tried to reproduce this in real life, but it was a failure. Don't worry, because if you add a pinch of salt to the mix and cook for a few minutes, you get this tiny flatbread. So, it was not a failure after all. But look, I spilled some water on the kitchen desk. Quick, let's clean up. Might not happen with flour, but a paper towel actually soak up the water. As you can see, this looks exactly how it looks on the trailer.
Now I need to clean up this mess. Damn it. This flatbread is really good.
This phenomenon is called the capillary action. The fluid can move without help of external forces in narrow spaces, like these paper towel pores, or between the gaps are virtual powder. The more narrow the quote-unquote tubes are, the easier it can move, due to the surface tension of the fluid and the adhesive force between the liquid and the surface of the structure. Under a microscope, we can see the small fibers, as well as how water fills up the small gaps between them. We can abstract this complex structure as a tunnel system with a bunch of intersections, where the fluid can move around the channels. And with one extra steps, we can abstract this as well as just nodes and edges, aka a graph, or in our case a constraint network, which is something that we can make and use in Houdini. Another important aspect of this effect is as the distance from the source increases, the speed of the spread decreases. In reality, this is true as well, but it's less dramatic. As you can see in this example, there's a notable difference how fast the fluid floods the paper towel at the beginning compared to the middle section. I'm not sure why this is happening. If you have any tips or the proper answer, I'm waiting for your comments down below. Actually, this is what makes this project especially challenging. On its own, creating a spread solver isn't difficult. The core idea is simple. Calculate the closest points to each point, and if the origin point have a specific attribute value, assign that value to the nearest neighbor. If you do this over time, you just make a spread solver. However, in this case, we need to slow down the spread as we move further from the origin. But I'm going to talk about this more in depth later on. With all that, I should stop yapping and start working on the setup. For starters, I need a geometry to build a constraint network for it. Maybe a bit simpler. More simpler, like a cube. Yeah, this looks good. Oh, for fuck. I converted a 3D shape to a bunch of points. The idea was to visit each point and check if there's any other points in a given distance. If there are, draw a line between the two. If we do this for the whole geometry, we end up with a network of points and edges. At least on paper. Yeah, so there's a small issue with the setup. If I try to remove, for example, this edge, you can see it's 78 and 175, meaning there's two edges on top of each other. And as you can see, they are actually sit on top of each other. The problem was that the connection array contains values back and forth. So the point zeros connection array was 0, 1, 2, meaning the script draws a line between 0, 1 and 0, 2. But for the next point, the array is going to be the same. So point 1 connection array is 0, 1, 2. Which means that here as well we draw a line between 1 and 0. So they're already two edges on top of each other. I added an extra condition here which break the loop if the endpoints, the lookup points, is greater than the current points, ptnum. In which case the draw function only called once per point pairs. Now we have a cleaned up network which is traversable. Why is it important to be traversable? You might remember that the spread gets slowed down as it moves further away from the source. The question is, how we knew how far certain points are from the source? Well, let me introduce the B.F.S algorithm, or breadth first search. This is a graph traversal algorithm which works the following. It starts at a given point, where it checks which points are connected to it, and put those into a list, which serves as a queue. Once that's done, it's put the original point to another list to know that it should be ignored to the later iteration. Then, remove the current point from the queue and pick up the first next item from the list and do the same with that one. This will continue until the queue is emptied out, meaning the graph is fully traversed. This is a straightforward task to do, even in Houdini. First, I promoted a single point to become the source, then wrote a VEX code that performs the BSF operation. It first checks each point to determine whether it is a source or not. If the point is a source, it's placed to the queue to start a B.F.S, which is just a simple while loop. In the loop, the point is added to the visited list, then the script looks for all the connected points. If a point is found that has been not visited yet, and it's not part of the queue, it's added to the queue. Once that's done, the examined point is removed from the queue, and the script picks up the next one from the list. But there's a huge difference between just traversing a graph and traversing a graph while we calculate the depth value of each point. To calculate the depth, I need to change the code. More specifically, I removed the visited array and introduced the visited dictionary. The reason was that the list is only contained the points I already checked without any extra information. But with the dictionary, I can store the point's number along with the corresponding depth. When the code looks up a neighbor, the point's number can be used as a key in the dictionary, and the value will be the current point's depth plus 1. Using this approach, we can now determine how far the points are in terms of connection from the source. With that knowledge, we can later on control how quickly the fluid should increase at each point. I was wrong. Let's remember what I said a few minutes ago. Another important aspect of this effect is as the distance from the source increases, the speed of the spread decreases. Yeah, that sentence was totally incorrect. If we only focus to the middle section, yeah, it feels like the spread is getting slower as it moves away from the source. But the smaller stream at the corner didn't even touch the powder, it just barely paints the surface under it. They probably use the quote-unquote simple spread solver with an attribute to control how many color a point can get with each frame. So there's no B.F.S, no depth search, nothing actually. And actually I don't blame them, because at the end of the day, their solution is just works. And in a production environment, it's more important to something just works compared to be robustic and realistic like my solution. Am I going to scrap the idea? No, actually, because I think that this is a really cool stuff and might be some use cases for it, so we should continue with the video. But why? I just finished this. Okay, let's go back. This took the most amount of time. The graph was slow. This shouldn't be a problem on its own, but this setup needs to run on multiple frames, with sometimes over hundreds of source points. So I need to come up with a few smart optimization technique. The first ones I already did previously. Namely, there's a slider in Vex node which limits the maximum depth the algorithm can go. So after a search reaches a certain depth, it just stops. But it was not enough. I need more. I started to think how the graph is designed, and I found the flaw. Currently, a single B.F.S handles all the source point calculation, which again, more of a design issue. But it would be better if each source point gets its own separated B.F.S algorithm, and then the results get merged. Give me a new title. A for each block in Houdini works like in any other programming language. You have a block of code, or in this case nodes, which are to be performed for each input element. In this case, I wanted to perform the BSF operation on each point. More specifically, on each source point, which is going to be problematic, because the for each block always follows the geometry's order. So if the sources are 45, 68 and 132, Houdini first going to do 44 useless operation before it reach a point which is an actual source point. Another problem is that the loop doesn't know when to stop. So even if it's reached point 132, the points after that still get processed, which increase the calculation cost. To prevent this, the for loop has a parameter called maximum iterations, which breaks the loop after a given number of iterations is done. If we go back to our previous example, where the total number of sources was 3, putting 3 to the maximum iteration, just visit the first 3 points, which none of them a source. We need to rearrange the point order temporarily, so the loop only goes through the sources. I used an enumerate sop, which creates an ordered attribute based on a group. Then, any point where this attribute is -1, just get the dummy values, which is the largest value plus 1, and use a subsort to create this new order. And with this, the maximum iteration now only goes through the source points. That's great, but the graph is still slow. So I start to look at the amount of sources we handle with each loop. There's a bunch of points which are covered by other sources. For those points, the B.F.S still get calculated, but they don't affect the output, because the depth we got from those points is always greater than the border source values. So those can be removed from the sources. This will reduce the number of B.F.S we need to perform, but this was not enough. At this stage, I started to think that doing 2000 B.F.S on a geometry which has more than 10k nodes might not be possible in a reasonable amount of time. But I keep pushing it further and took a look at the most resource-heavy component, the Vex code itself. I started to clean up and refactor the code and did a bunch of iteration on it. I even asked ChatGPT, but as usual, it just hallucinates non-existing Vex functions. So that was a dead end. This was the point where I started to give it up. Oh, wait a second. Multithreading. If this and only then, and maybe you get multithreading. Oh, come on. I mean, what can I lose? Well, I don't think this is multithreading. I noticed something. If the code never tries to set any attribute on the geometry, the search is fast. Like, really fast. And then, I remembered. Under the hood, each node stores the geometry locally, and when we change something on it, it's recooked. This is an important optimization, so the changes only affect the current node and everything above. When we try to push the data to the geometry, Houdini immediately recooked the geo, which took time. So the question was, how can I avoid to push data to the geometry and still get my result? My final idea started to take shape in my head. It involved not pushing data to the sources and multithreading. But first, I need to do some RTFM, or read the funny manual, so I actually took time and read when a for each loop can support multithreading. It requires the following. Each iteration must create new geometry, so it shouldn't rely on the previous iteration. Which is obvious. You could not calculate two things parallel if one is reliant on the other. It should fetch the input and not the feedback. Same reason. And finally, it must need to be in a compiled block. But why and where do I want to use multithreading? Well, splitting a single B.F.S to multiple processes might not be the best idea. But because there's multiple B.F.S, it is possible to send each of them to a separated thread, and once all of them are calculated, collide the results and set the respective points depth attribute based on the collided dictionary. I started to experimenting with multi-threaded for loops. Earlier, when I first dipped my toes to the topic, I abandoned the idea, mainly because I tried to run the loop in an input geometry, resulting in millions of points. But now, because I know that pushing data to the geometry is the main bottleneck, I need to come up with a smarter solution. After some try and error, I made this simple setup. Currently, I have a geometry which contains roughly 1 million points, with a random value assigned to each point, as you can see. The goal is to select a random floor and ceiling and calculate the average value between that range 2000 times. By default, this is going to be a slow process because here we push the data to the geometry. So you can see it took a bunch of time to write the data and to do the process. And finally we have the last average value. But here comes the trick, because we can use multi-threading this graph here. So what's happened if I try to let's force the node to be recooked, and as you can see, this is 100% faster and we get all the results here. So this is 2000 points containing the average calculation of each loop. Now, besides from being in multi-threaded mode, I also modified how the graph is behaved. So in the first version, we actually processed the full geometry. But here, instead of doing that, that is just a simple reference. The first input actually only contains a single point at the origin. This will be our data container. And what is happening inside this loop is that the point is get processed once, the loop is over for the first iteration, it's fetch the origin point again, do the process again but with the second iteration number, and keep continue this until we reach 2000. And the end result, because we set this to merge each iteration, will be 2000 points with the results. So now I just need to refactor my graph based on my example and do the collision part. Once that was done, the calculation became fast, so finally I can go to the next section. Right? Now the search is working in a single frame. It is time to wrap it to a solver, so it's going to work across multiple frames. This is a piece of cake compared to the previous suffering. I grabbed the algorithm and just tossed it to a subsolver. Most of the things already done, I just need to prepare for the next frame. Once the B.F.S is completed, I restore the point order, reset the attributes, and emptied out the source group, so the B.F.S in the next search won't use those points. Unlike the B.F.S solver, this one does not require any in-depth optimization. It's more about shaping the final look of the effect. This solver is going to handle how the fluid attribute is distributed among the points. It checks if a point's fluid volume attribute is greater than the threshold. If it is, start to increase the neighbor point's fluid volumes, which start a chain reaction. The amount of how much the neighbor fluid is increasing each frame is calculated by the following formula. The neighbor point's previous fluid volume plus a constant global flow rate multiplied by normalized depth or normalized suffering multiplied by edge resistance and multiplied by external resistance. Most of these values are just normalized floats. The two interesting things is edge resistance and external resistance. Edge resistance is a random float in each edge to break up the evenness of the spreading, while external resistance on the other hand is a user-defined attribute which the artist can use to have a better control over the fluid movements. There's not too much to talk about this section. In fact, originally I wanted to cover this topic in a short form video, but as the project and the B.F.S solver compile time growth, I realized this could be an interesting long form video. For the last step, I packed the two solvers into a subnetwork and added the most important parameters to it. I also tried to replicate the powder from the trailer, but I failed. So instead of dust, in my render, styrofoam soaks up the fluid. And if you wanna explore the setup, you can find a heap file on my Patreon. The heap file contains two subnetworks, one to convert the geometry to a constraint network, and the B.F.S infection solver. And with all that, this project is considered to be finished. It's a relief that after many years I was able to replicate the original one, and now I can start working on my next project.